I want to revisit a question that's been asked in the past in a couple classes, and that's how long is a transmission line? When do we have to use transmission line analysis versus lumped element amount analysis like we've been using in previous classes? And I had told you previously the answer is lambda over 10. Well, where did that come from? So in these figures, what I've done is I've plotted the magnitude and the phase of the load voltage for two conditions. One is when we connect a voltage source with an internal impedance to a load, and we model the interconnect using lumped element, and that is plotted in black in both these plots, this dashed black line. And then we've plotted the same source and same load. We've plotted load voltage, but if we use and load voltage, magnitude, and phase, but if we use a transmission line model of length d instead. And what I've done is I've calculated load voltage for a lot of different values of d. In fact, I've let d go from lambda over 100 all the way up to 10 lambda. And using the more advanced transmission line model, what we see is that at low lambda, all this voltage gets delivered to the load, 100% of the voltage gets delivered to the load, and there's no phase shift. And according to transmission line theory, that stays pretty much true. And then what happens is, as the transmission line gets longer and longer as compared to wavelength, we get this oscillatory behavior. And that same behavior is not predicted by the lumped element model. So the correct value of the voltage magnitude at the load is given by this blue line. The incorrect value, as predicted by lumped element analysis, is given by this dashed line. And we see that they start separating appreciably right about here, which is lambda over 10. And so for values of transmission line length that are less than lambda over 10, we see that the lumped element and the transmission line model give us about the same value. Whereas above that, they really start to separate, and we can't rely on lumped element model analysis anymore. It gives us incorrect results. We see that can also be extended to the phase shift. We see that lumped element analysis does not correctly estimate what the phase shift will be. We get this oscillatory behavior in phase shift. Really what's happening is phase shift is just dropping off really, really fast after about, lambda over 20 here. Sorry, lambda over 5 here, about that. So that's where this value of lambda over 10 comes from as a rule of thumb, is because of the magnitude difference. So for transmission line lengths below lambda over 10, we're good. We can use either model. For transmission line lengths above lambda over 10, we cannot count on that model. We have to use T-lines.